I'm starting a later lecture. Okay.
Yeah, I have started the recording.
Okay. So last lecture we saw the definition of effective orthogonal symmetric algebra, and depending upon that, we define this when a Riemannian symmetric is really compact type, non-compact type, Euclidean type. We have also really uh, discussed that we saw the definition of symmetric space of compact type, non-compact type, and Euclidean type. So in today's lecture, I will really the thing is I will give some example of Riemannian symmetric space. Before that, I have to tell something. So a little bit of discussion first. So discussion. So the thing is, suppose let G be a connected Lie group. With Lie algebra of G is G. Suppose okay, then we know that this thing. Then int G, I have defined this thing. Int G is really RG. Okay, because G is connected, and we know that this thing int G is subset of odd G. Okay. So int G is really this thing is odd G. Okay. So now the killing form BG is int G invariant, odd G invariant. Therefore, it is since odd G is subset of odd G, this is really odd G invariant. Okay, so this is a piece of important information. Okay, so let okay, again this is a part of this one. Let G, S be a Riemannian symmetric pair. So then this odd G H, okay, this subset of odd G and this subset of odd G. Okay. So let G is equal to K plus P be the corresponding quadratic composition. Okay. So now if you look at this thing, so BG, this since therefore BG restricted to P cross P is RGH invariant because RGH is subset of automorphism G and killing form is RG invariant. So BG restricted to PP is RGH invariant. Now we have two cases.
Now, Mona, say it again. What is the significance? It is BGG restricted to P cos P is RG invariant.
Acha, BGG is the RGH invariant. Okay, that is the. So if I restrict this BG to P cross P, this is also RGH invariant. This is trivial because. So what?
Yes, but
What is
somehow
what
this
is the?
means that P is RG invariant.
No, killing form is RG invariant. What does this mean? Okay, so let me do.
That is okay. But when you are saying it is restricted to this is RG invariant.
Because P is I have shown that this P. Okay, that is an important point also. I have shown that this thing RGH P is really the subset of P.
Yeah, then it makes sense. Yeah.
Actually, okay, so this is really. So this is the thing. Now, so we have two cases. So case one. So let the RSP GH is effective and is of and is of compact type. So then that means this BG restricted to P cross P is really negative definite. Okay. But if I will take this minus BG restricted to P cross P, so this is an RGH invariant inner product on and any such inner product which is RGH invariant that induces a G invariant Riemannian structure on G mod H. So hence minus BG restricted to P cross P induces a G invariant Riemannian structure Q on P cross P is so that this Q naught is equal to really minus BG restricted to P cross P. Here actually what is O, where this O is equal to this S, this belongs to G mod H. And I have told you that I can identify this P with T naught G mod H. So I am using under that identification, I am saying that Q naught is equal to minus BG restricted to P cross P. Okay. So now we have second case, case 2. Case 2. So let G comma H be an effective Riemannian symmetric pair of non-compact type. Okay. So that means by similar argument, BG restricted to P cross P. This is always positive. This is positive definite by definition. This induces a G invariant Riemannian structure Q on G mod H, so that this thing happens. So that Q naught is equal to really BG restricted to P cross P. Here where this thing O is equal to really H belongs to G mod H. And we have also identifying here T naught G mod H with really P. T naught G mod H with P. And this is an isomorphism. Hence, I have the following remark. So, remark. So, let G comma S be an effective Riemannian symmetric pair of compact or non-compact type. Compact or non-compact. Then unless specified, if you are not specified about the Riemannian structure of G mod H, then you will always assume that the Riemannian structure on G mod H is induced from the Killing form. So then unless specified, we always assume that the G invariant Riemannian structure on G mod H is induced from the killing point. So this is the thing. Now again, different type of discussion. So let M be the Riemannian manifold Rn, and N is Riemannian manifold Rn. So then if you look at the product manifold, M cross N is really Rm plus N. Okay. Now the thing is, if you look at this Im cross N, and you look at the connected component of Im cross N, so this is really Rm plus N, semi-direct part SO M plus N. Okay. And if you look at this Im naught, this is really Rn SOM, and In naught, this is really Rn. So you can check this thing. Check that. So dimension of Im plus dimension of In, Im naught, these are same. Im not equal to really dimension of Im cross N. In general, for small n probably this will M is equal to 1 or something. Probably they might be same, but it is not same in general. Okay, so therefore I in general. Okay, I am writing in general actually. You have to check for M is equal to 1 or N is equal to 1 probably. I do not know. Therefore, this Im or N naught is not really isomorphic to Im naught cross In naught. This not isomorphic. Sorry. This means not isomorphic. Not isomorphic. From this you can. So this also implies that Im cross M is not isomorphic to Im cross In. Okay. So this is not isomorphic. Okay. So hence it is true that. So conclusion: if M and N are Riemannian manifolds, it is so in general it is not true that this Im cross N naught is isomorphic to Im cross In naught and this thing. This symbol means isomorphic. So this okay. So now yes, sir.
I just wanted to see it easily that it's not isomorphic. Isn't it hidden in the fact that SON has some dimension like n into n minus 1 by 2 and something? Because
Yes, sir.
SON plus SOM will not be SON plus n because of that complicated.
Yes, sir.
That's why things
Yes,
are going wrong.
Yes, sir. So because of SON. So this is the thing. Now we really, so last time we have seen that, okay, recall. Actually, I have given an exercise there, then that is a very easy exercise. Recall, we have seen that the following let this following proposition. I am writing it in a proposition, but that's okay. That G1 H1 and G2 S2 are effective Riemannian symmetric pair of same type, same mu, okay, say mu. Then the product G1 cross G2, H1 cross H2 is an effective Riemannian symmetric pair of type mu. That means if G1 and H1 and G2, S2 are of compact type, say, then their product is also of compact type. If they are of non-compact type, then their product is non-compact type, like that. Okay, so discussion. So let G, H be an effective Riemannian symmetric pair of type mu. So question. So can we conclude that the Riemannian symmetric pair, Riemannian symmetric space M is equal to G mod H is of type mu? So that is the thing. So see, the thing is to show that M is of type mu. So by definition, what I have to look? I have to look for this symmetric pair, this IM not and this stabilizer of something. Okay, some stabilizer of some P, where P belongs to G mod H, right? I have to look at this symmetric pair. Okay. So, but the thing is, since hello,
Yes, we can hear you.
hello.
Yeah, I can hear you.
Yeah. But you are not able to see my screen, or what? Hello,
Yeah, I can see.
you can see my screen.
No, not that write up that you have to present again.
Yeah, I can see the screen, but not the write up yet.
It will take some time, I think, because
Now I can see
internet.
the write-up.
Now I can
Yeah.
see.
Okay, thanks. So where was I? So why I was discussing? Hello, Annoy?
You are posing this question,
Yeah,
Madhav.
Okay, can you conclude this? Okay, so what is the thing? Let G, H be an effective Riemannian symmetric pair of type mu. Can you conclude the Riemannian symmetric space M is equal to G mod H is equal to type mu? Okay. So if you look at the definition of when this Riemannian symmetric space is of type mu, so for that we need this Riemannian symmetric pair where this G is equal to really I am naught, and this K is really some stabilizer of some P in M. So this symmetric. So you have to really check whether this symmetric pair I am naught and K is of compact type or non-compact type or something like that. Okay, but yeah, yeah. No. So see, the thing is G mod. Okay, that will be H eventually. Okay, sorry. Okay, this is really stabilizer of O inside G where O is equal to H. Okay, that's okay. I am not H. Okay. So this is I have to look the this Riemannian symmetric pair. Okay, but it is not always true that G is equal to really. No, actually, yeah. No. Okay, so just wait. Sorry. Okay, I so no. That I was doing right. So you look at this G. I should not really use the same notation. So I have to do. So the question is, so let me start from the beginning. Let G comma H be an effective Riemannian symmetric pair of type mu. Can we conclude that the Riemannian symmetric space M is equal to G mod H is of type mu? Okay. So to show that this is really of type mu, so we must look at the Riemannian symmetric pair I am naught and the stabilizer of P inside this I am naught. This symmetric pair. But I am not sure, we are not sure that G is really I am not or not. I have given some example where G is not I am not. And okay, so this was the main problem. But and the example what I have given that is really falls in this Euclidean type category. If you look at that example, so this answer is yes if. So answer yes if mu is either compact or non-compact. For a Euclidean thing, you cannot really conclude. Okay, so or I have okay. So this is the thing. Okay. Now you will give some example of symmetric spaces of Euclidean type. Yes, sir.
Hear me?
No, I cannot hear you properly.
Can you hear me now?
Yes, sir. Now I can hear you.
Yeah, I was just trying to say that usually the isometric group could be bigger than G, and in the Euclidean case, perhaps we are dropping the reflections. So I could have taken ON instead of SON. Will that give me a counterexample in the Euclidean type? I have forgotten that what example you talked about.
No, actually, yeah, not SON actually. I have taken any subgroup of suppose SO, okay, Rn cross any compact group, this L, okay, where L is a compact subgroup of SON.
SON, okay.
Suppose you are really in the SO5 say, so you can take SO4, SO3, you can take L is equal to SO3, SO4, L is equal to identity also. So all this, is this example is clear, sir?
Yes.
So SON I am not taking ON because ON will not be connected, and
Yeah,
by the definition
connectedness
of
is a
Riemannian.
problem. Yeah, connectedness
Yes,
is a problem.
so this is the thing. Okay, so let us start from the Euclidean type. So example. But the thing is, this is not a bigger problem because we always know what are the Riemannian symmetric space of Euclidean type. We will know shortly. So example of RSS and RSP of Euclidean type. So first example is, of course, your m is equal to Rn, and here G is equal to Im naught is equal to really Rn semi-detached product SON. Then okay, you look at this K, then K is equal to really stabilizer of G inside O. Oh, stabilizer of O inside G is isomorphic to SON. What is the group law here? This VA dot WB is really V plus AW. This is AB. Okay. So A comma B belongs to SON and VW belongs to Rn. So Lie algebra is G is equal to, this is Rn cross small SON. So now you look at this thing Vx, Wy. This Lie bracket is, you have to calculate this thing. So this is really XW minus By. Actually, this is really Lie bracket of XY. So this is my Lie bracket in this thing. It needs little work. You can try this as an exercise. So then the involution sigma from G to G. So this is the thing XY belongs to small SON. SON is the Sioux symmetry matrix and VW belongs to really Rn. So sigma from G to G is given by this thing. Sigma of Vx, Va. This is really minus Va. Okay. And so let theta is equal to d sigma. So I want to calculate this theta. So let Vx belongs to G, and so therefore let Vx belong to G. Let gamma be a curve from minus epsilon to this G, so that this gamma prime 0 is equal to really Vx. So let gamma t is equal to gamma 1t, gamma 2t. So if you define, so from this thing you will get what? Gamma prime 0 is equal to really gamma 1 prime 0, gamma 2 prime 0. So that means Vx is equal to gamma 1 prime 0, gamma 2 prime 0. This thing, gamma 1 prime 0 is equal to V, gamma 2 prime 0 is equal to X. So theta of Vx, this is equal to d by dt of t is equal to 0, sigma composition gamma t. This is really d by dt. So since gamma t is really your gamma 1t and gamma 2t, so that will give you what? Minus gamma 1t, gamma 2t, right? So this is really minus the gamma 1 prime 0, gamma 2 prime 0. This is really minus Vx. So you can also do this thing, you can avoid this calculation. Just observe that this extends to some linear map on a higher dimensional manifold, which is a vector space. So you can do that thing. Okay. So but theta of Vx is equal to minus Px, hence P is equal to x belongs to okay, x belongs to okay, Vx belongs to G. So that theta of Vx is equal to minus of Px, right? But theta of Vx is what? This is really minus Vx, right? And this is really minus V minus A. So that means x is equal to 0, right? This implies. So P you will get what? So P is really, this is really B0, so that B belongs to Rn. Similarly, K you will get this thing that K you will get this thing 0 A, so that okay, not A, so I should write X, so that X belongs to SY. You can do that calculation. Now, so let V1 0 comma V2 0, this belongs to P. So you look at this V1 0, V2 0. This Lie bracket is, if you look at this expression which I have given, so that will be actually 0. Hence, Lie bracket of PP is 0. And this is a really equivalent way of saying that this Riemannian symmetric pair is of Euclidean type. And I am taking this full isometric group here for the symmetric space Rn. So, and hence, and I have shown that if you are taking this full isometric group and the stabilizer, that is always an effective Riemannian symmetric pair. Hence, this thing what Rn SON, and this is SON, is an effective Riemannian symmetric pair of Euclidean type. And Rn is a hello, are you able to hear me?
Yes.
Suddenly I lost my connection. I am sharing my screen once more. What will happen? Just wait for 2-3 minutes. Actually, I have to. It seems that I have to log out, and then I have to enter once more. Just wait.
Then is still, I mean, others. Can anybody hear me? Hear anybody?
Yes, sir, we can hear you.
Oh, okay.
Yeah, the internet connection at HRI is actually fluctuating. That is the
Okay.
problem.
Okay. Okay. So I'm always worried whether it is problem from my side.
So are you able to see my screen now?
Yes, Honorable.
Okay, thanks. So, something really happening strange. Okay, so this hence this is an effective Riemannian symmetric pair of Euclidean type. Okay, so if okay, for those who may not be who joined little late, so I have to just tell you something that which Manoj Da has asked and Swagat Rai sir has explained. So in the last lecture, actually Manoj Da asked that if G H is a Riemannian symmetric pair of Euclidean type. Okay, so let me write them. So this was the question he was asking. If GH is an effective Riemannian symmetric pair of Euclidean type, whether G is solvable. This was the question. I am not explaining what is solvable. You can just see the definition later. So it is true that if okay, so G is solvable. So what is that definition? So you can G is solvable. Sorry, G is solvable if and only if this Lie algebra is solvable. You can see this definition later. So if you take G is equal to really this thing Rn plus SON, this Lie algebra is really Rn and the small SON. This okay, and one knows that if this G is solvable, any sub-algebra of G is also solvable. G is solvable. Now this small SON is really a sub-algebra of G. Now one knows that if n is equal to, for n greater than equal to 5, this SO okay, so SON is solvable. Actually, if you just include this 4 case, then exclude this 4 case, it will not solvable. Sorry, it is simple. So and simple Lie algebras cannot be solvable. So for that reason, this G is not solvable. Hence, G is not solvable. Actually, you just see the definition, you will get it. That is a nice. Actually, this is a nice answer. Okay, so now, so second example. So second example is your S1. S1. If you look at G is equal to really I of S1 not, and this is really SO2. This is really abelian Lie group. Now, if you look at this thing, this point 1, this SO2 acts like rotations. So if you theta, if you take any non-trivial rotation, that will really rotate the point 1. So if you look at this K is equal to stabilizer of G inside 1, then this is really identity. Okay, since this G is abelian, this implies this Lie algebra is abelian. So that will imply this P is 0. Okay. Hence, this thing SO2, this one is an effective Riemannian symmetric pair of Euclidean type, and S1 is a Riemannian symmetric space of Euclidean type. So hence this observation is our warning. You can take that thing. So this non-compact Riemannian symmetric space. So let us write in the grade. So non-compact Riemannian symmetric space. For example, Rn is a Riemannian non-compact Riemannian symmetric. That doesn't really mean that is a RSS of non-compact type. So these are two different terms: non-compact Riemannian symmetric space and Riemannian symmetric space of non-compact type. These are really two different terms. And this compact, similarly compact RSS, this doesn't really imply that RSS of compact type, because you have seen that S1 is a compact Riemannian symmetric space, but this is not a Riemannian symmetric space of compact type. Okay. So third thing is, if you look at this thing SO2, I told you that if you G1H1 is a Riemannian symmetric space pair of Euclidean type, and G2, S2 is a Riemannian symmetric pair of Euclidean type. If you take the product, then that is also a Riemannian symmetric pair is of Euclidean type. So then this SO2 cross this thing as Rn. Okay, sorry. This is cross this thing SON. This is really SON. This I should write this to E cross SON, but that is isomorphic to SON. Is a Riemannian symmetric pair of Euclidean type. So, however, I cannot conclude from this thing. So, however, we can conclude directly that the corresponding Riemannian symmetric space is what? Riemannian symmetric is really S1 cross Rn is of Euclidean type. And this the problem was this thing, that whether this this problem was this thing. I explained you that we cannot directly conclude that I am not region. Okay, so let me write this. So there are two reasons. First one, we are not sure that whether this thing happens. This I of this thing I of S1 cross Rn is your, whether this is same or not, and it will be not true actually. This result is it is very unlikely that this result is true. But there are some So this was not a thing, and because this thing is, and so this is the precise the reason. Okay. Okay. So, but however, a remark. However, it is true that this S1 cross Rn is a Riemannian symmetric space of Euclidean type. Okay. So also it is known that any Riemannian symmetric space of Euclidean type is of the form this thing S1 cross S1. This is k times into some r to the power n, and any simply connected thus okay, and okay, and any simply connected Riemannian symmetric space of Euclidean type is isometric to Rn. So actually what one does, one actually proves something called, if something is a symmetric space of a Euclidean type, one proves that curvature is really identically zero. And there is a theorem in Riemannian geometry which states that any simply connected complete Riemannian manifold which has curvature identical zero is really isometric to Rn. And using those facts and a little bit of covering space theory, one proves this result. So I am not going to do that, but we have really discussed every Riemannian symmetric space of a Euclidean type. You can just trust me on this result. Now we will really.
So it's basically the above list is basically the all abelian Lie groups, right?
All abelian.
Lie groups. S1 product of S1 and then Rn.
Yeah, that is the other way.
So it is same as the all symmetric space of Euclidean type.
Any connected abelian Lie group. Actually, Helgason doesn't define even this so-called symmetric space of Euclidean type. There is a reason for that, because this is the reason, because you know everything.
Okay.
So now I want to state a proposition. So we want to really go to example of compact or non-compact. The first proposition I want to really tell about. Okay, so let GH be an effective Riemannian symmetric. Then G, H is of type mu. Okay, where mu is here, I am including compact or non-compact. I am not including Euclidean. Okay. So then G, if and only if the corresponding Riemannian symmetric space M is equal to G mod S is of type mu. Okay, so this is really the thing. So proof I will do this proof later, or you can just, I am writing this to be shown later, but okay. So you will use this thing, and using this proposition and the fact which I have told in this proposition, okay. Using this proposition and this proportion, let G1, H1 and G2, H2 are effective RSP of types and type. Then G1 cross G2 and H1 cross H2 is an effective RSP of type mu. So using this two proposition, it is not difficult to see that this proposition. So actually this is not a proposition. So let M1, M2 be a Riemannian symmetric space of type mu, where mu is really compact or non-compact. Compact. Okay, mu belongs to. Okay. Then their product, then Riemannian product M1 from M2 is of type mu. If M1 is a Riemannian symmetric space of non-compact type and M2 is of non-compact type, then M1 cross M2 is of non-compact type. Okay. So now little bit of discussion. So let G be a Lie algebra over K. So let X belongs to ZG. So this will imply that RG X is equal to 0. So that means B of XY is equal to 0 for all Y belongs to G. This implies ZG sits inside radical of B. Okay. So hence we have two corollaries. So first corollary is really let G be a semi-simple Lie algebra. So then this implies ZG is equal to 0. Okay, so corollary 1 and corollary 2. So since we let G be a semi-simple Lie group, so then ZG is discrete because this small ZG is equal to 0, therefore this ZG is discrete. This is easy to see. Okay. So now one proposition. So let G be a compact Lie group. So then following are equivalent. So first G is semi-simple. The second thing is ZG is finite. That's in the Killing form of G is negative delta. That means Killing form of G means Killing form of the Lie algebra, right? It's negative definite. I have proved part of this theorem. So we prove actually I have shown that equivalence of 2 and 3. I have shown that if ZG is finite, then Killing form of G is negative definite. And I have proved that if Killing form of G is negative definite, that means G is semi-simple. Okay, so it was in page 632 or something. Just really. Yeah. So here actually page 631, let G be a compact Lie group with center ZG, then Killing form B on G is negative definite if and only if ZG is finite. And this thing also proved that. Okay, so if G Killing form is negative definite, then G is semi-simple. I have proved that. So part of the thing I have proved probably. So 2 and 3 is things, and 3 is also implied 1. I have proved. And 2 is also implied 1. I have proved this. 2 is implies 1. I have proved. So let G be semi-simple. So that means ZG is discrete. So this implies okay, and also ZG is compact. Since ZG is closed, subgroup ZG is closed in G, and G is compact. This implies ZG is compact. So as ZG is both compact and discrete, therefore ZG is finite. This implies ZG is finite. So we have this is really the thing I implies to. So this is for that. See page 631 and page 632. Okay, so this is the thing. We will use this thing. Okay, so now discussion. So let G, S be a Riemannian symmetric pair such that G is a compact Lie group and this ZG is finite. So that means ZG intersection H is also finite. So if you a Riemannian symmetric pair is effective and only ZG intersection H is discrete, and it is we are getting this is a finite subgroup. So this implies so GH, the Riemannian symmetric pair GH is effective. Okay. Now as ZG is finite and G is compact. It's compact, then therefore this BG is really negative definite, right? Hence, and we have, if you have followed my previous lecture, this precisely an equivalent condition of that of a Riemannian symmetric pair of compact type, right? This implies GH is an effective RSP of compact type. Okay, so we will use this thing. Okay, so if G is a compact Lie group, so that ZG is finite, then this G, S in a equatorial Riemannian symmetric pair of compact type. So let us see first example. Okay, so this is the Riemannian symmetric pair of compact type. And what about the Riemannian symmetric space? Riemannian symmetric space. I have told you that proposition. If the Riemannian symmetric pair is of compact type, then the symmetric space is also compact type. You can use that thing. So and okay, and the RSS. G mod H is of compact. Tapendra, is it clear?
Yes, Honorable.
So Muna, this symmetric pair space of compact Euclidean type, they always have curvature 0, right? External curvature.
Yes.
And this compact type and non-compact type, they will have.
So I told you that
Positive or negative.
Positive, but this will not be identical.
No, my guess is compact type will have curvature positive and non-compact type will have curvature
Strictly
negative.
positive. Strictly positive will not be. Yes. This is greater than equal to 0 and not equal to 0. identical not equal to 0 and somewhere positive. And there will at least okay. So let us start from examples. RSP and RSS of compact type. Okay, so actually I will take some matrix Lie group examples, but you know that suppose some thing is sub G is a subgroup of GLNC or something like GLNH or GLNR. These are the groups we have really discussed. So if you look at the center of G for the time moment, you just assume that this is contained inside lambda I, so that lambda belongs to the field. Lambda belongs to C or H or R. Okay. Probably we will prove this all these things. But the thing is time for the time moment, because we have to eventually calculate the center. For that reason, you just assume that thing. So first example is really, you know, this SON, this thing S of OK cross ON minus K, right? This is really 1 less than equal to K less than N. Okay. So Z of SON, this is really identity.
This is the Grassmannian example, right?
Yes. This okay. So a plus minus identity, and this identity if N is really okay even and N is odd. But the thing is, you have to exclude the case N is equal to 2. So N is greater than equal to 3. You can take. So hence, and this is finite here. So Z of SN is finite. This is finite. Hence, this thing and SON, this thing SOK cross ON minus K is a Riemannian symmetric effective, is an effective Riemannian symmetric pair of compact type, and this Grassmannian thing GR, what was the notation? GRKN. Okay. GRKN is a RSS of compact. So you have to take this restriction 1 less than equal to K less than N and greater than equal to 3. For N is equal to 2, this Z of SO2 is whole SO2. Therefore, you have this restriction. And second thing is, I have told thing. So this is, let us write this thing. So this is SON. This is really SOK cross SON minus K, and we have the same thing. 1 less than equal to K less than N and greater than equal to 3. So this center of SON is finite, hence this thing SON plus SON minus K is a RSS of RSP, is an effective RSP of compact type, and the RSS here actually, what is the RSS? Oriented Grassmannian. GRK not. What was the notation? The GRK not RN or something? Is of I actually forgot the notation. GRKN or GRKRN? Okay, GRKRN I think, because yeah. So sorry, GRKRN. Okay, so one special case. This thing, you take this N is equal to K is equal to 1. So this GR1 not Rn is what, for K is equal to 1, this is really SON This is SON mod SON minus 1. So this is really SON mod SO1 cross SON minus 1. This same thing as SON mod SON minus 1. And this is same thing as SN minus 1. Hence SN minus 1 is a RSS of compact type. Now second thing, this third example. So you look at this thing, SUN mod SUK cross UN minus K. Okay, so similarly we have this 1 K less than or equal to N, and this is N greater than or equal to 2. So here
Muna, I have a silly question. So it may be obvious. So if you have a symmetric space of compact type, will it be compact?
Compact type, yeah. For that reason, actually, I didn't really hear actually. So this
Because the
direction is
examples
true.
we are seeing, they are
Yeah,
compact.
yeah. This is really in this direction it is true. Okay, so there are too many things to do actually, but I don't have much time, so this is true actually. Compact. Okay, so SUN, this is the thing. Now Z of SUN is really this lambda I, so that lambda to the power n is equal to 1, and this is really Z mod Nz, and this is a finite group, right? This is finite. And hence this thing SUN SUK cross UN minus K is a Riemannian symmetric pair of compact type, and in this case this was the complex Grassmannian, and the corresponding RSS GKCN is of compact type. Okay, so next example is interesting. See, the thing is GKCN has two representation. Okay, so I have really GKCN. You can look at this thing like okay, so let us GKCN. You can really look at this thing as SUN mod SUK cross UN minus K, and this was really UN mod UK cross UN minus K. These are two representations. This is also a symmetric pair. So let us see that symmetric pair. Four. So this UN UK cross UN minus K is a Riemannian symmetric pair for GK7. This is 1 less than equal to K less than N. So if you look at this Z of UN, this Z of UN is really lambda I. So the mod lambda is equal to 1. Okay, this is really isomorphic to S1. And when this Z of UN, if you look at this intersection UK plus UN minus K, so this is really same thing, lambda I, so that mod lambda is equal to 1, and this is really isomorphic to S1, and this is not discrete, right? This is not discrete. Hence this UN comma UK, oh god, I left some places, UN minus K, okay, is not an effective Riemannian symmetry. Effective Riemannian symmetric pair. So this is not an effective Riemannian symmetric pair. For that reason, it is not useful. Okay. Okay, let us is not an effective Riemannian symmetric pair. Moreover, this center is center is not discrete. Moreover, observation that UN is not also semi-simple. Observation this UN is also not semi-simple, as this center of UN is not discrete. So this was the thing. Fourth example. Let us give me the fifth example. Fifth is the same thing. You know that UN and okay. So now fifth is really, you know that this SPN, this thing SPK cross SPN minus K. This is really 1 less than equal to K less than N. And the thing is, if you look at this Z of SPN, center of SPN, this is what? This is actually, this will be subset of Q, so lambda I, okay, QI, so that Q belongs to H. This is Q is a Q belongs to H, and since QI belongs to SPN, so this will be sort of norm of Q is 1. Okay. But H is quaternions are non-commutative, so QI, Q and Q prime I, this may not be Q prime I into QI. So that, so for that reason, actually it will be something like, it will be plus minus identity. Okay. So, and this is finite. Hence, this SPN, SPK cross SPN minus K is an effective Riemannian symmetric pair of compact type. And this GKHN, okay, GKHN is the quaternion Grassmannians of K planes in the HN. The GKHN is a Riemannian symmetric space of compact type. So 6, let us see. 6 is also interesting. Let us see. UN. I have told you that UN ON is a Riemannian symmetric pair. Okay. If you have followed my thing, that what was the involution here? Sigma A is equal to A bar. So okay, is an Riemannian symmetric pair. Now Z of UN is really lambda I. So the mod lambda is equal to 1. Now if you look at this thing, Z of UN intersection ON. So now you are taking intersection with real matrices. Those, for that reason, that will be cross minus identity, and this is finite. Hence the Riemannian symmetric pair is effective. Hence the RSP UN ON is really effective, but neither of compact type or non-compact type. The reason is this UN is not semi-simple. What is the reason? Reason is this UN is not semi-simple. Reason UN is not semi-simple. So 6, 7. So let us see. 7, this same thing, UN mod SON. So this is UN SON is an effective. You can check that the thing is an effective Riemannian symmetric pair. It is an effective Riemannian symmetric, but neither of compact or non-compact type. So now, so let us see the next example 8. This thing, you look at this SUN mod SON. So Z of SUN, this thing is, so lambda I, so that lambda to the power n is equal to 1. And this is finite. Hence, SUN, SON is a Riemannian symmetric, is an effective Riemannian symmetric pair. Of compact type. And SUN mod SON is a Riemannian symmetric space is of compact. Now I have taken another example I have given. So did I left something? You look at this thing SO2n UN. These are actually, so this SO2n mod UN is really is an effective Riemannian symmetric pair of compact type because center of SO2n is finite, and this SO2n mod UN is a Riemannian symmetric space of compact. So if you know a little bit of geometry, these are really, you can identify this SO2n mod UN with a oriented orthogonal complex structure on R2n. And similarly, these have also geometric meaning. SU, some Lagrangian subspace or something like that. SU1 mod SU1. Okay, so this is the thing. Did I left everything? Or left? Okay. So now, so let G be a compact Lie group with finite center. Then we know that then G cross G, delta G cross G is a Riemannian symmetric pair with corresponding RSS is G. So hence corresponds. Now what is Z of G cross G? This is really isomorphic. This is same thing as ZG cross ZG. And since ZG is finite, so this is finite. Okay, hence.
What is that notation? Delta G cross G?
Okay, delta G cross G. So recall delta G cross G is diagonal in G cross. This was the thing. So this is finite, and this, and also, okay, since G cross G is compact, this thing G cross G delta G cross G is an effective Riemannian symmetric pair of compact type, and G is a Riemannian symmetric space of compact type. So for therefore examples, you can produce like more like something like SP N, SON, and this is really SUN. You can also take Cartesian product of something like SOM to the power K1 plus SOM1 to the power K1 and SUM2 to the power K2 into SPM3 to the power K3 are example of RSS of compact type. Actually, you have to take here n greater than equal to 2, right? This thing for this thing n greater than equal to 3. And what about SUN? SUN n greater than equal to 2. Something like that. SP1. SP1 is P1. Okay, that is okay. So this is n greater than equal to 1. So some trivial cases you have to really exclude. So okay. So now, as you know that, so since product of two Riemannian symmetric space of compact type is a Riemannian symmetric space of compact type is a Riemannian symmetric of compact type. One can produce one can produce a lot of examples. Produce more examples. So more examples. For instance, this thing here GKRN cross SOM, whatever product you can take that, you can produce that. So I wanted to do this complex structure, but the internet connection was really okay. So I don't think that I will continue more. I could not do more things today. Okay, if there is any question, you can ask me now. In the next lecture, actually, we will discuss about the Riemannian symmetric space of non-compact type. But the thing is, for proving a Riemannian symmetric of non-compact type, there are some ways. For instance, duality is where you prove that if you are taking a Riemannian symmetric of compact type, its dual is non-compact type. So by that, you can produce some example, or you prove that if some Riemannian symmetric space is irreducible, then it will be of compact or non-compact type. Then that is also another way. But since we do not know much theory, we will really prove a Riemannian symmetric space of non-compact type by directly calculating the killing form. Okay, so and we have to really compute the killing form for 2-3 some examples at least. So and tomorrow and in the next lecture we will do that. So then we will see how. So we will see what can be done. Okay, so with this, I would like to stop. And if there is any question, you can ask me. Anwar, Ushab, Tapendu.
Fine, no questions.
Okay.
Hello, Munala.
Yes.
Could you go to the last lecture before on the definition of orthogonal symmetric Lie group, Lie algebra?
The definition of orthogonal symmetry. Rajasthan, are you recording?
Yeah, recording is on.
Okay, don't stop the recording. Okay, so
Okay.
questions are important. Okay, what is that? Okay, effective orthogonal symmetric algebra, something like that. So definition.
Before the definition, there is some statement.
Just wait. Orthogonal symmetric algebra. Better. Okay, this is the definition that.
Just before that, K is compactly embedded Lie subregular G. It follows from you said that at GH is compact. I couldn't
Okay.
follow how it's being followed.
So actually I have discussed, you can see the last recording. Okay, so let us see. So where I have told you. Actually I have discussed this thing in detail. Okay, so just wait. Just wait, I am showing the page. Okay. Yeah. Suppose RG is this page 621. Okay, I have discussed this thing. Page 621. Let G be a connected Lie group. With Lie G and H be a Lie subgroup of G. With Lie algebra of H is equal to H. Suppose RG is compact. Then H is compactly embedded G. In for the connected Lie group, this was statement. Okay. But the thing is, for non-connected group, if when H is non-compact, also I have told you. Just wait. Just wait. So where is that? Page 621 or something. It's 21. G with Lie algebra. Suppose RG is compact, then yeah. See, the thing is here actually. So if H is not necessarily close connected, look at the page 620. So if you then I have shown that this K is H is compactly embedded in G. K is compactly embedded. In page 620, you see that if you will not, you are not able to follow, then tell me. You look at the recording actually. Is there any question?
No, nothing from.
Hello, RPS sir, Rudra sir. Hello, my sir.
Are you talking to me?
Yes, sir. Yes, sir.
Yeah.
How are you, sir?
I'm all right, more or less.
So I didn't see you in 2-3 lectures.
Yeah. There was some problem. Moha had COVID again.
Oh God. Oh, you. What about you?
I suppose I didn't get so far.
So can I
But
see
I
you?
was
Sir?
busy managing that.
Oh. Can I see you, sir?
Yeah. Just wait.
Sir.
Yeah.
So now everything. Now everything. Yes.
Yeah.
Only your eyes. I can see you.
Only eyes. Okay.
Now everything is fine, sir.
Yeah. Okay.
Probably
So how
the
many
There is a
lectures?
post-COVID effect.
I think I will